Okay, questions, comments? All right, I think this mathematized question is the last technical little fact that we need. And the mathematized question tells you what happens when you add random variables, what happens to the mean and the standard deviation. And if you know this technical fact, then you can do all sorts of cool things, including that dice problem that I was doing last class. So let's take a look and see what you guys said. So you roll 2 dice. The first dice is x1, the second dice is x2. Of course, x1 and x2 are identically distributed, so they both have the same distribution of outcomes, but they're 2 independent copies. Independent, you see I spelled it independent. So that's what we call IID random variables. What is its mean and its variance? And we know the original mean and variance was mu and sigma. What is the transformed mean and variance? I keep saying variance. I should keep saying standard deviation. We know that's the important one. Okay. I'll say one more quick thing. Mean and standard deviation have the same units. Like if x1 is some number of meters and x2 is some number of meters, and the mean is also measured in meters and the standard deviation is also in meters. That's why these are nice. The variance has the units squared, which is kind of annoying. That's why we do standard deviation. Okay, no more wasting time. Let's see what you guys said. All right. So first one, mean mu. Second one, mean mu. Add them together. Everybody knows 2 mu. Amazing. Great job. What about the standard deviation? So this one we've seen before, actually. The real point of this question is just to do the second one, the standard deviation. What did people say for this one? And this one, 39 people know, it is square root of 2 mu. And that's the right answer. I'm very impressed that so many people knew. I thought I would trick you all into saying 2 mu, or 2 sigma, but it is square root of 2. And this is, I think, a really surprising thing, that when you add the random variables, the standard deviations do not add. They get a square root of 2. There is one other thing in your life that you have seen before that is like this, which is if you add vectors together. When you add vectors, if you add one vector like this, so this is the vector, let's call this vector the x-axis vector, and you add this to the y-axis vector, even if the length of x is 1 and the length of y is 1, and someone says, please tell me the length of x plus y, and this is the situation where the length of x is 1 and the length of y is 1. What is the length of x plus y? Very tempting to say it's 1 plus 1. It's not 1 plus 1. It is square root of 2. And that's because you have to use Pythagoras' famous theorem that the things add, and when they add, you get this square root business. You get a square root of 2. And this square root of 2 really comes from the square root of 1 plus 1. Okay. And standard deviations are exactly like this picture. So if you're ever wondering where this weird thing comes from, it's the same kind of idea. Standard deviation is some kind of length, how big the vector is in some sense. And standard deviations also do this. So this is like a fact about standard deviations. The standard deviation of x1 plus x2 when they are independent, they square some add. So that's the standard deviation of x1 plus the standard deviation of x2, and you square them and you add them together with a square root. So it's like a Pythagoras formula for the standard deviations. And in our case, if both of these things were sigma, you get sigma squared plus sigma squared. Hold on. This part can be the fact. This is like the Pythagoras formula for standard deviations. Pythagoras for standard deviations. And then let's do our little mathematized problem as the little warm-up example. If the standard deviation of x1 equals the standard deviation of x2, then you get, let's call that sigma, you get the standard deviation of the sum x1 plus x2 is the square root of sigma squared plus sigma squared, also known as square root of 2 times sigma. So the standard deviation grows, but not by a factor of 2 like you might expect, but by a factor of square root of 2.
Mihai, I have
yes.
an interjection here.
Absolutely.
So the standard deviation, one of the beauties of the standard deviation is that it is in the same units as the original variable. But why do we mess around with variances then? Why do we have
That's a great question.
why do we mess around with
Let's investigate what would happen if we look at the variance.
So the thing with means is the mean of the sums is the sum of the means. The variance of a sum, if the variables are independent, which is a necessary condition for variances, if the variables are independent, the variance of the sum is the sum of the variances.
Yes. Okay. So actually, this fact that we just did, right?
And that's what you did. You did the sum of the variances, and then that gave you the so the sum of the variances gave you 2 sigma squared. That is the variance of x1 plus x2, and then when you took the square root, you got the.
That's right. So the fact is stated with standard deviations because standard deviations are useful, right? They tell you they're in the original unit, and they tell you what's going on. I really should not write vectors over here. I think I got a little vector happy. Let me delete my vector signs. So it's stated in terms of the standard deviation because standard deviations are useful. Let's translate the fact. Let's write it in terms of variances instead of standard deviations. And that's because the standard deviation and the variance are exactly the same thing except one is the squared of the other. So this is fact version 1 and fact version 2 is exactly the same thing, but let's write it in terms of variances. And so to get the variance of x1 plus x2, you square the standard deviation. And so that would be this thing squared. That thing squared exactly undoes the other side. So it's the standard deviation of x1 squared plus the standard deviation of x2 squared. Okay, but the standard deviation squared has a name. It's the variance. So you could equally well write the variance of x1 plus the variance of x2. In other words, the variances add, even though the standard deviations Pythagoras add. And this is when x1, x2 are independent. x1, x2 are independent. This is a bit like in the original geometry picture. One way to describe the Pythagoras rule is you would say when you add perpendicular vectors, the length squared add. Right? The length of the hypotenuse squared is the length of the bottom squared plus the length of the side squared. They square add, which is, we have a name for the square. It's the variance, so the variances do add. Okay, I can't resist proving this because it's actually a very simple proof. So here's a quick proof of fact 2, or I guess it's the fact version 2, which is identical to fact version 1, just stated in a different way. And I'm going to do it in the case where the mean is 0. And the case where the mean is not 0 is exactly the same, except it's just a little bit more writing. And so I'm not going to do it. I'm just going to pretend that the mean is 0 and not worry about it. It just makes it a little easier. All the vibes are exactly the same. And the reason it's so nice is because when you do the variance of x1 plus x2, that is simply the expected value squared. It's the expected value of x1 plus x2 squared. If you were in a different case where these things were non-zero, you would have to subtract off the mean. So it would be a little bit more annoying, but this is a nice, easy case where it's super simple. This is a great place to stop. So we've stated the statement. Now we're doing a quick little proof. This is a great place if you're confused about what we're trying to show. You can let me know. All right. How would you do this? You see x1 plus x2 squared. Now you know why they tortured you in high school with FOIL. I like the little rhyme, square the first term, square the last, double the product, math's a blast. That's how I do it. So in this situation, it's x1 squared plus x2 squared, square the first term, square the last, double the product, math's a blast. Okay, great. And now we have an expected value. We got sums. Expected values play nice with sums. You can split it up. It's the expected value of x1 squared plus the expected value of x2 squared plus 2 times the expected value of x1 times x2. Okay, these first two terms, these are great. We can deal with these. That's because we're assuming things are mean 0. So in this mean 0 case, the expected value squared is exactly the variance of x1 plus the variance of x2. That's wonderful. What about this dopey term over here? The expected value of x1 times x2. Oh boy. Anyone have an idea on how you would deal with this kind of term? Yeah.
Root x1, x2.
Say that again.
Root x1, x2.
It's the square root of x1, x2. Like this?
It's like that, yeah.
Well, okay. So you have to deal with the expected value. You want to put the expected value under the square root, or?
Like the variance of it.
Ah, okay, yes. Okay, this is very good. I see what you're saying. You're saying this is the variance of something. So you're saying that it's the square root of itself squared. So you could write it as the variance of the square root of x1, x2. Yes, okay, this is a great idea. So this is a nice way to convert it into a variance. It turns out this would probably work. Eventually, I think if you chase this down, you would eventually get it. It turns out there's an even nicer way to get this one. And there's a simpler thing you can do that will simplify it. So this is a good idea. I think this will work, but there is an even simpler thing you can do. And I will give a hint. And the hint is we are assuming that they are independent. Maybe on your formula sheet, when things are independent, there's a special little trick we can do. Yeah?
You can have expected of x1 times expected of x2.
Exactly. So this is where the independence comes in. When we have the product of two things, if the two things are independent, we can split them up because of the independence. So the independence means we can simplify by one more step. It's 2 times the expected value of x1 times x2. And random variables that do this are called uncorrelated. If they're independent, they're definitely uncorrelated. It's definitely okay to split them like this. So this is a nice simplification. And in fact, it gets even easier. This is an extra simple thing in our case. Does anyone know what this is equal to? Yeah. 0. In fact, it's not only is it 0, it's 0 squared. This term is 0, this term is 0. I guess it's 2 times 0 squared. We assume they were both 0. This whole thing is 0. So this is 0 equals, or 0 times 0 by assuming expected value of x1 equals 0. So this whole thing was 0 by the assumption. If you do it in the general case where this is mu and mu, what you're going to get here is a quadratic equation with mu, and after factoring it, you'll find the same conclusion. So the proof I gave technically only works in this special case, but if you do the same exact thing in the more complicated case, you will also see the same proof. So this is a proof of sort of Pythagoras for random variables. If you take linear algebra class, you'll see a Pythagoras formula for any inner product space. That's what you do in linear algebra class. In fact, some of you might notice if you're a fan of trigonometry, you might remember there's a term in the correction to Pythagoras called the cosine law. The cosine law. This little term over here is like the cosine law term. In the case where they're perpendicular, the cosine is 0. All right. So that's the proof. That's why variances add, and that's why standard deviations Pythagoras add. And I think this is the last very technical formula we're going to need in the course. You should be able to use this formula. You don't need to be able to prove it. We're showing you the proof because, damn, it's cool. Okay. Questions or comments? All right, let's see how to do this in action. And the reason this is such an important rule, and it's so useful, is because it is useful for, quote, normal approximations. Normal. And this is what we were working on last class. We had a few of these. We did one where we rolled 22 dice, and we said, oh, that's approximately a Gaussian, or approximately a normal distribution. And then we had one where we were looking at binomial random variables, and that's approximately normal. But always, when you do a normal approximation, what you're going to do is you're going to say, take a random variable. Let's call the random variable x. And you say x is approximately the normal distribution with mean. What should the mean be? Well, it should be whatever the mean of x is. And what should the standard deviation be? Well, it should be the standard deviation of whatever x is. The standard deviation of x. So when someone does a normal approximation, they're saying, this x is way too much work to deal with. I'm going to replace it with this super easy distribution. I'm sure you guys feel, when you're looking at that complicated table, that the normal distribution is the simplest of all the distributions. But it turns out the other ones are even worse. So this is a nice thing to do because this one is relatively simple. You have the table for it, and so you can calculate things with it. So that's the approximation we do. And as an example, what about rolling 22 dice? Here's an example. We could roll 22 dice. So we could do dice 1 plus dice 2 plus dot 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 plus d22. I guess. Okay, let me not call them d because dn was a dice with n sides. Let me call them. Let's call them y1, y2, y22, where each yk they are iid fair six-sided dice. That's exactly what I did at the beginning of last class, where I rolled 22 dice. I had 22 outcomes, and the way I calculated things, I was able to answer questions about this weird sum of 22 different dice by just saying, hey, it's approximately a normal with what is the mean? Well, the mean we know how to do. The mean we said is 22 times 3.5 times 3.5, which was 77. That was last class. And the reason it's 22 times 3.5 is every single dice contributes at 3.5. The 3.5 is the average of the numbers 1 to 6. It's the average of any individual dice roll. When you add up 22 of them, you get 22 times 3.5, or 77. That was the mean. And now you know the technical formula. You will be able to find the standard deviation. So the standard deviation of this random variable, adding up a bunch of dice rolls, y1 all the way up to y22. Before you knew the fact, maybe you would have done this wrong. You would have said it's 22 times the individual standard deviation. But now you know it is actually the square root of 22 times the individual standard deviation. So it's the standard deviation of any individual dice, let's say y1, times the square root of 22. And that square root is exactly what we just showed with standard deviations. You could also say the variance was 22 times higher, and so the standard deviation goes by the square root of 22. So that is the fact. We can do a little exercise and calculate exactly what this is. Maybe I'll do that in a second. But is the factor of square root of 22, is it clear where that came from now? So that is the Pythagoras in action. Yeah, question at the back.
Where did you get 22?
The 22 is because I said we're rolling 22 dice. This was roll 22 dice. So if the problem says roll 22 dice, then that's where it came from. If a different problem says roll 10 dice, then you would have 10 instead of 22. Great point. Other questions? Yeah?
This is assuming that we know that X is already approximately all of it.
Yes, so this is the thing. Very famous quote that has already come up like 3 times in this class. Some models are wrong, other models are useful. And it turns out this normal approximation thing is often very useful. I will tell you in particular, there is a special reason it works nicely for sums of things. So there is, we'll see that in a second. So it's extra justified. If the thing you are doing is a sum of random variables, then everybody will be like, yeah, thumbs up, normal approximation, great job. If the thing you are doing is some other thing, you can still say, I'm going to try a normal approximation, and maybe you can get people to agree with you. It's like harder because there's no nice theorem. But in general, you can always do it. And in particular, I don't want to disparage the statisticians who are sitting right over there. But they very often do it, and they're just like, yeah, it's normal. Just don't worry about it. Would you say that's accurate?
No, that's not accurate. Not accurate. Not accurate.
Under what circumstances are you okay with saying something is normal? Let's hear of applying the approximation.
The thing is, so the thing you'll see in your next stats class, Stat 2040, etc., there'll be a discussion of the central limit theorem. And the basic idea of the central limit theorem is that if you take a sufficiently large sample, which is equivalent to having a sufficient number of these IID random variables.
Why don't I pause you for a second? Let me write down what the central limit theorem is, because that was the next thing anyway.
Well,
so
this thing is the central limit theorem has a precise definition, which we don't actually write precisely.
Sure. Okay. So let me write down the idea of the central limit theorem. And once again, there is an excellent 3 blue 1 brown video idea of the central limit theorem.
Yeah.
Which will give you all of the juicy, fun parts of the central limit theorem in beautiful animated form that is well beyond what anyone could do in a class. But it's truly beautiful, and will give you the main idea. And basically, the idea is normal approximation is valid for sums of independent random variables. Approximation is valid for sums of independent. And really the whole rub is, what does is valid mean? What does this mean? What does is valid mean? What does it not mean? And I will tell you the very technical definition is a fat arrow definition, which says if you add up x1 plus ... plus xn, so this is a sum of n independent random variables, and you divide it. Remember last time I was saying when you're doing approximations, you gotta normalize it. If you just added these up, they would explode. They would just get bigger and bigger. That would not be good. In the examples we saw, we divided by n. In this one, you got to divide it by square root of n. And the reason it's a square root of n is exactly the square root that appears over here. But this normalized thing, this will fat arrow converge to a normal distribution of mean mu and variance. Let me write it out in words. Normal with mean mu and standard deviation sigma. So if you properly normalize things by dividing by square root of n, then they will fat arrow converge to sigma. Fat arrow means the distributions get closer and closer together. We saw the fat arrow convergence for dice converging to a uniform. Technically, it's called convergence in distribution. And that's the statement of the central limit theorem, or at least the idea of it. And it sort of justifies why normal approximation is okay. So we won't ask you to do anything with fat arrow converging, but we will ask you questions like, I rolled 22 dice. Use the normal approximation to calculate the probability it's less than 80. It would be just slightly over a half. Okay, but now you can finish saying, how do statisticians feel about this?
So the trick about it is you've got the sums of the independent random variables, and how quickly the distribution of the sum or the distribution of the average approaches a normal distribution depends on what the underlying distribution is.
Yeah, so in other words, in the thing that's written on the board here, this is really a statement about the limit as n goes to infinity of x1 plus ... plus xn over square root of n. This in some sense equals a normal. If you can talk about the limit equals something, and statisticians are worried about, okay, as n gets bigger and bigger, eventually it'll be normal. But do you need 100? Do you need 1,000? Do you need 1 billion? Do you need 20 billion? How big does n have to be before these are close?
So the n is really the number, is really related to the sample size you take. And first of all, essentially you rarely take a sample that is tending to infinity. So it's generally a lot smaller than that. And then the question is, how small can it be? And it really gets down to how non-normal are the underlying random variables, the distributions of those underlying random variables. So it can be extremely small for a lot of distributions that are not that far off of normal, or even something like the uniform distribution converges to approximate normal for the sums very quickly. But I can also come up with, make examples where a sample size of 1 million is not sufficient to get approximate normality. But we'll leave that one till next semester.
So in other words, it's a mathematical statement that the limit as n goes to infinity equals the normal. But the mathematical statement of the limit is not actually helpful. If you want to actually do stuff, you got to say, look, I did 1,000, and it's actually close. And if you're taking calculus, you'll know these limits can be quite slippery and quite subtle. It's like, how big does n have to be? It's like a little bit like, how small does your epsilon have to be? So it's a kind of an existential question. The mathematical thing that's quite nice to prove is the limit as n goes to infinity. And then the real life useful thing is let n be some large finite number. Is it close? That's the useful thing. And there's like a kind of a tension between these two things. You can make upgraded theorems that say like how big is the error and stuff, but then it gets quite hard. But yeah, so this is the central limit theorem and what it's talking about. All right. How did we start? Someone asked us a question. We've just been talking for 20 minutes. This is great. Any other questions? You have a chance to take up the whole rest of the class if you ask a good question. This is very embarrassing now. If you ask a question, I answer it in 1 second. Okay. All right. So where were we? This was the central limit theorem. There is one thing I want to point out in addition to the central limit theorem, which is kind of cool. So the proper way to normalize is the square root of n in the central limit theorem. And that is equivalent to looking at the standard deviation over here and noticing that the standard deviation grows not like n, but like square root of n. Let me show you that example that we had last class. Let's see if I can find it. It's going to be in one of these. Where will it be? Maybe in this? Nope. Maybe in this one? Yeah, okay, here we go. I found it. Hidden amongst the many, many tabs. Okay, this is what we were doing last time. And so the thing that we were doing last time is we were rolling the dice. And as you roll more and more dice, it's well approximated by this normal approximation. So this is rolling 22 dice. But the nice thing is I have a slider of the number of dice, and we can see what happens as you roll more or less dice. And the thing that is interesting is that if you plot the mean and the variance here, let's plot the mean and one standard deviation. Let me get rid of this purple region and the labels. Okay. So I'm plotting a dashed green line at the mean, which is 3.5 times the number of dice I roll. And I'm showing you +1 standard deviation and -1 standard deviation. This is the region that contains like 70% of the sample. And the fun thing to do this class that we didn't do last class is to vary the number of dice and make some observations. So let's go between 5 and we said 22 dice rolls. Actually, if I tone this one down, let's only repeat it 100 times, and I can go all the way up to, say, 40 dice rolls. I can go up to 100 dice rolls. Okay. So what I want you to see is, as we're varying this, what is going on with this distribution. So this is the blue histogram is like real life samples, and the purple is the approximation. All right, and we're rolling some number of dice between 0 and 100. And as you roll more dice, of course, the mean gets bigger and bigger. It occurs to me these histograms are not very helpful. They're just kind of like some chaos on top of the approximation. So let's take it for granted that the histogram is well approximated. Let's just look at the actual curve. So when you roll just a couple dice, you have a very narrow thing. When you roll more dice, it's a higher mean. And the thing I want you to notice is what is happening to that standard deviation. The standard deviation gets bigger as you roll more dice, but it's not growing as fast as we are moving. And what this means is that if we were to sort of zoom out and look at sort of this x-axis, not on a scale from 0 to 350, but on a sort of a fixed scale where this wasn't moving, then things would be interesting. So that's what I'm going to do next. Let's do that now. How do I do that? What do I want to do? Okay, this was for dice. Let's do the binomial one. I think it'll look better on the binomial one. And for the binomial one, let me save this thing and open up the binomial. We're going to see the same exact thing on the binomial. Okay, so this was the binomial distribution we were doing last time. And last class, we were varying the p-value. So the p-value can be very small, could be very big, and the point is that as long as p is not really close to the end, like really close to 0 or 1, in the middle, it is pretty well approximated by normal. So these are actual binomial probabilities with that n choose k formula. And here is the normal approximation. And the normal approximation is right on the money when you are kind of in the middle. It's not so great when you're very high. So this is the binomial. This is what we ended on with last class. Same idea as dice. If you roll enough dice, you don't need to worry about the individual details. It's always a normal approximation. You can just do everything that way. So that was varying the p-value. I'm going to, in a second, vary the n value. And I want you to notice what happens when I vary the n value. But before I do that, any questions on what this is showing? Make sense? So let's vary the n value. And I need to tell you an important detail about the scale here. a binomial is always between 0 and n. It can't be smaller than 0. It can't be larger than n. It's somewhere between 0 and n. And I have automatically scaled things so that 0 is over here, and n is always over here. So if I double n, it's still going to be here, and everything will just get smooshed closer together. So right now, n is 57. This represents n equals 57. If I double it to 114, what will happen? This is now 114. So basically, I doubled n, but all the bars got closer together, but this range still represents 0 to n. And now we can say, what's going to happen when I make n bigger and bigger? And the obvious answer is it's going to melt my computer eventually, but let's see how big we can make n before that happens. And why don't we fix a p-value somewhere in the middle? Let's do p equals 0.7. That's a nice little thing. So the n value right now is 114. The p value is 0.7. This is about 70% of the way between here and here. 70%. Nice normal distribution. What happens when we increase n? Place your bets. Oh, okay. So the things went away. So first of all, it's shrinking. And the other thing you should notice is it's getting more narrow. So the shrinking I can handle. I'll just blow it up by a factor of n. So why don't we blow it up by a factor here? Let's zoom in on the y-axis by square root of n. And now let's do it one more time. So we'll start at 0. And let's do it one more time. So here's 30. And now you'll notice it's shrinking. It's getting more and more concentrated. So what is the moral of the story? When you do a normal approximation, it works perfectly. But when n gets large, it's actually concentrating around the mean value. So now it's increasing again. This is shrinking. The computer melts down for the binomial variables and only shows us the approximation. And the thing I want you to see is that when you scale things, so it's a scale from 0 to n, things are shrinking. This is another famous theorem. So the theorem of these approximations is called the central limit theorem, and it says that the normal approximation works when you divide by square root of n. The theorem, the observation that things shrink, so observation, the distribution shrinks around its mean. The way you could write that is you could do x1 plus ... plus xn, and don't divide it by square root of n, but divide it by n this time. So when you divide by n, you really are doing the actual average of these random variables. And this is getting closer and closer to not a random number, but always a constant. And that constant is mu, whatever the average was. And what this is saying is, actually it's a normal distribution, but the normal distribution is getting so concentrated it might as well be a single value. So for example, in my little example over here, I had p equals 0.7, and it's saying if I take a binomial random variable with a very large n, as n gets bigger and bigger, the fraction is getting closer and closer to 0.7. So the value of the binomial random variable divided by n gets closer and closer to 0.7, and as n gets larger and larger, the limit is literally equal to 0.7. Maybe I'll say one last cool little buzzword. Not only does it fat arrow converge, it does another type of convergence called almost sure convergence. That's the AS convergence. That's almost sure. And if you do the almost sure, this is called the strong law of large numbers. So this convergence is called strong convergence, and this is called the strong law of large numbers. And it is super related to the central limit theorem. The central limit theorem says it's a normal distribution. The law of large numbers says if you divide by n instead of square root of n, then it's going to shrink down, and it's going to be a number, not even a random thing anymore. So in this one, it was a random thing, and this one is not random because you shrunk it so much, it concentrated down to one single number. Okay, we'll do more of this stuff on Friday, and we'll do some review problems as well, and then you'll have a few weeks to study for the exam. Okay, let's stop there.